Welcome to the 20th quarter of complex numbers. Here in this 20th quarter, we are going to deal with the radius of convergence of power series. In this quarter of radius of convergence of power series, we are going to learn the ratio test. We'll deal with some examples. We'll understand the root test. Then again, we'll find some examples for exploration. Then we'll learn the Cauchy Hadamard criterion, which is above the ratio test and root test. Analytic function and power series correlation we are going to learn, which is a very powerful technique. Then we shall deal with some examples. Power series. Now let us recall the idea that we have developed in the previous lecture. The given power series AK into z minus z0 to the power k, where k rolls from 0 to infinity. This is a power series. For this power series, there exists a number r, which is having some value between 0 and infinity, such that the series converges, of course, absolutely if that complex number z is within the radius r from a reference point z0. Otherwise, it diverges. Now, here we are talking about the complex plane, and in that complex plane, consider z0 to be a point. Now we are talking about the set of all complex numbers whose distance from z0 is less than radius r. Let us suppose that this is a circle of radius r, and we are talking about some number z which is in the close vicinity of z0 such that mod of z minus z0 is less than r. Now, if the point is lying within the circle of radius r, then the power series converges. Otherwise, it diverges. Now the question is that how do we find that radius r? On what parameter it depends? It goes by this theorem. There's a ratio test. If the sequence ak upon ak plus 1, note that here this ak is a complex number. Ak upon ak plus 1 mod has limit. If this sequence has limit as k approaches to infinity, then this limit is the radius of convergence of that power series ak z minus z0 to the power k. Here you should note that infinity is the allowable limit because r is permitted to have any value between 0 to infinity. Let us now roll through some examples. Here goes the first one, z to the power k, where k rolls from 0 to infinity. Now we can compare this with the basic definition of the power series, that is ak, which is a complex number, into z minus z0 to the power k. Now here you can identify that this ak is unity. By multiplying 1, it does not make any difference. So ak is 1, and z0, this quantity is 0 in our case. So according to the theorem that we have discussed in the previous slide, ak upon ak plus 1, modulus of that, and here all the coefficients are unity, so 1 upon 1 will be 1, and as k tends to infinity, the limit value tends to unity, and therefore that limit value is the radius of convergence. So here we have r is equal to 1. Now consider k into z to the power k, where k rolls from 0 to infinity. Now ak, that is the coefficient we are talking, it is equal to k, and ak plus 1. If you like to see this coefficient ak plus 1, it will be simply k plus 1. So we have to obtain the ratio modulus of that ak upon ak plus 1, that will be k upon k plus 1. Now here you can divide numerator by k and denominator by k. So this limit offers unity value as k approaches to infinity, and therefore as the limit value is 1, the radius of convergence is unity again. Here goes next example, z to the power k upon k factorial, where k rolls from 0 to infinity. That's our series, and in this series ak, the coefficient, which is a complex number, that is equal to 1 upon k factorial. Now the next number in the series will be ak plus 1, and that k plus 1 will be k plus 1 factorial. Now here we have to obtain ak upon k plus 1. Now if you like to write ak, it has value 1 upon k factorial, and that is divided by 1 upon k plus 1 factorial. So this turns out to be k plus 1 factorial upon k factorial. So you can write this k plus 1 factorial as k plus 1 into k factorial divided by k factorial. I'm writing it in short so that I can process as I desire, and here you can cancel k factorial in the numerator and denominator. So we are left with k plus 1. Now as k approaches to infinity, k plus 1 also approaches to infinity, and therefore the radius of convergence is infinity. Now let us consider the next example, z to the k upon k to the k, where k rolls from 0 to infinity. Here ak is 1 upon k to the k, and ak plus 1 will be 1 upon k plus 1 to the power k plus 1. And then we have to take the ratio of ak upon ak plus 1, and after considering the ratio we obtain k plus 1 to the power k plus 1 upon k to the k. Now this is a little not obvious number in terms of limit when k is approaching to infinity, and we have to work it out. Numerator I am trying to operate k plus 1 I am considering into k plus 1 to the power k. So here I have split that number, and in the denominator we have k to the k. Now we can take k plus 1 as it is, and then we can write inside bracket k plus 1 upon k, whole thing to the power k. We can further rewrite this to obtain the form. I'm writing the first term again k plus 1, and then 1 plus 1 over k, whole thing to the power k. So this is not obvious thing that we deal in terms of limits, but definitely it is solved in calculus, and this quantity has limit e, that is Euler's number, and this number k plus 1, it has limit infinity if k is approaching to infinity. So infinity into e, so the limit of this is infinity. So the radius of convergence is infinity. The kind of problem that we have discussed just now, we should have a root test run for that, and whenever we have ak is equal to 1 upon k to the k, it is easier to have this root test. And what this root test theorem says, if the sequence of kth root of mod of ak has a limit as k approaches to infinity, then the radius of convergence is equal to 1 upon limit k tending to infinity kth root of mod of ak. So we have to obtain the limit, and we have to find the reciprocal of that to obtain the radius of convergence. Now it is obvious that if the limit k approaching to infinity kth root of mod of ak, if that is equal to 0, then reciprocal of that is the radius of convergence, and if this limit is 0, then radius of convergence is infinity, and otherwise if the limit is having infinite value, then the radius of convergence is 0. To understand this test, let us go through some examples. Now let us deal with this example z to the k upon k to the k. We have already worked out this, but we are now using the root test theorem for this. And the root test theorem talks about inverse of the limit of kth root of mod of ak. So here we have to identify ak, and ak is 1 upon k to the k. Now kth root of mod of ak, it will be simply 1 over k, and as k approach to infinity, this value approaches to 0, and the radius of convergence is inverse of the limit. So 1 upon limit that offers us r equal to infinity, that is the radius of convergence is the circle of infinite radius. In this example, k into z to the k, where k rolls from 0 to infinity, and ak, this coefficient which is a complex number, is k, and we have to find kth root of mod of ak, that is kth root of k, and in fact this approaches to unity as k approaches to infinity, and therefore the radius of convergence is unity, which we have seen in the earlier case by ratio test. In this next example, we have 2 to the power k into z to the power k, again k rolling from 0 to infinity, and ak, the coefficient term, which is a complex number, is 2 to the power k. So kth root of mod of ak, it will be kth root of 2 to the k, that is 2. And as k approaches to infinity, the limit value approaches to 2, and by this theorem r is equal to reciprocal of limit. So it is reciprocal of 2, that is 1 by 2. Now let's consider this series minus 1 to the power k divided by 2 to the power k into z to the power 2k. Here we have to identify the coefficients, and a2k, the even coefficients I am talking about, that is equal to minus 1 to the power k upon 2 to the power k. Now to understand this, we should in fact first write down this series. We should expand this series, and if k is equal to 0, anything raised to 0 becomes unity. So the first number is 1. Then when k is equal to 1, we have minus 1 to the power 1. So this is a negative number, minus 1 over 2 into z square. The alternate terms will be plus and minus. So the next term will be plus 1 by 4 z to the power 4 minus this 4 minus 1 over 8 z to the power 6 plus 1 over 16 and z to the power 8 and so on. So you can go on expanding the number of terms. Now here you can see that only even powers of z, they have non-zero coefficient, and odd powers, they are not appearing. So the coefficients corresponding to the odd powers, that is a2k plus 1, they are 0, and ak2, they are minus 1 to the k upon 2 to the k. Now by the root test we have to obtain the 2k root of mod of a2k, and if you plug in the values you will be able to see that it is 1 upon under root 2 for all k greater than or equal to 1. And when the coefficients are odd, the powers of z are odd, and these coefficients are disappearing, they are not appearing, so their value is 0. So here we have a sequence which oscillates between 0 and under root 2, then back 0, then under root 2, and so on. So this doesn't have limit. So the limit is not existing. The ratio test will also tell you that AK, we have worked out AK 1 over root 2, and that divided by AK plus 1. So this quantity is 0. So in the denominator we have 0. So this is infinite, has no limit either. Now to handle this same problem, minus 1 to the power k upon 2 to the power k, z to the power 2k, where k rolls from 0 to infinity. We are handling the same problem, but now in a different way. We are not going to apply the root test, nor we are going to apply the ratio test. We shall let that z square is being replaced by w, and the series, if you replace z square by w, your series becomes minus 1 to the k upon 2 to the k w to the power k. And here the coefficient of your series, it is under root of k minus 1 to the power k upon 2 to the k, and this has value 1 by 2 when k tends to infinity, when k approaches to infinity. So now we have a new series that converges when mod of w is less than 2. Thus the original series will converge when mod of z square is less than 2, or you can say mod of z is less than under root 2. So in this pretext we have a new formula that is called as Cauchy-Hadamard criterion. According to this Cauchy-Hadamard formula, the radius of convergence of the same power series that we are discussing since this beginning of this lecture, ak into z minus z0 to the power k. So the radius of convergence is limit k approaching to infinity superior of kth root of mod of ak. If you find that there is no if and but, so neither root test we are bothered about, nor the ratio test we are bothered about. Without any condition, we can find the radius of convergence. Now, here we are going to understand how the analytic function can be developed using power series. This is quite interesting. Let us recall the power series AK into z minus z0 to the power k, where k rolls from 0 to infinity, and we are taking summation over all terms. And this is analytic in the radius, in the disk of radius r, centered around z0. So here capital R is the radius of convergence of the power series. This we have learned. Now let us consider a set U, and we have a function f that maps to a complex plane, and let us suppose that this function is analytic. Then consider a disk of radius r, little r, centered around z0 in the set U. So here you can consider some set U, and let me call this a set U, and in this set U we have a disk of radius r centered around a point z0, and we can consider any point around this z which is within the disk of radius small r. So I want to mention this is a disk of radius small r, and this disk is contained into the set U. That is what is mathematically mentioned here. Let in this disk we have a function f, and this function f can have a power series representation, that f of z is equal to ak into z minus z0 to the power k, where k rolls from 0 to infinity, and here we have z minus z0, that is a disk of radius small r centered around z0 we are considering, and here we can find out this coefficients ak of the power series for this function f of z, and this coefficients ak are kth derivative of f obtained at z0 divided by k factorial. Here k is the order of derivative, and it is presumed it is greater than or equal to 0. Either you are not finding the derivative, or you are finding first order derivative or second order, and so on. So the radius of convergence of power series capital R is greater than or equal to small r. Here capital R, we are talking about the radius of convergence. So if you are talking about a power series and you are within the radius of convergence of that particular series, then any function, now here I shall presume another disk of some radius, and in this disk again we can have the representation in terms of power series, and that representation may vary. Now let us suppose that f of z is a function that is represented in terms of a power series ak into z minus z0 to the power k, and here we are talking about a disk of radius small r which is centered around z0, and we are talking for all those points which maintain this criteria of residing inside the disk of radius small r. And here, according to what we have discussed in the previous slide, the coefficients ak are kth derivative of the function at center of the disk z0 divided by k factorial, provided k is greater than or equal to 0. Now let us deal with a simple example wherein f of z is equal to e to the z. This is a very simple function. Its derivative is the same function, and if you like to find kth derivative of this function, it will be again same e to the c. Now for simplicity we shall plug in z0 equal to 0. So center of the disk is the center of origin, and kth derivative at z0, which is 0, in fact we have e to the 0, and e to the 0 is always 1 for all values of k. Therefore we can work out this ak value, which is equal to 1 upon k factorial for all k. Now that we can write e to the z is equal to summation z to the k, and this time ak, which is in fact 1 upon k factorial, we have just now found. We can plug in here, and here this is true for all values of the complex numbers in the entire complex plane. So you can consider the complex plane, and you can consider a disk of radius r, and this r can go any longer up to infinity, and this power series expression e to the z is analytic within the disk of radius r, where r is infinity, so entire complex plane. And therefore for e to the z we can write summation k from 0 to infinity z to the k upon k factorial. Similarly, let us roll through similar example with a minor difference. Function is f of z is equal to e to the z, and here instead the disk being considered at origin, it is considered at z0 equal to 1. That is, it is intersecting real axis. Sorry, the center of the disk is at unity on the real axis, and kth derivative of the function, it will be e to the power 1. Earlier it was e to the power 0 equal to 1. So e to the power 1, we shall call this as e for all k. And therefore we can write coefficients now as ak is equal to e upon k factorial. Here it was simply 1 upon k factorial. Here it is e upon k factorial. So for this situation, we have e to the z is equal to summation e upon k factorial. So to write this series for z minus z0, here z0 being 1, we have written z minus 1 to the power k, and this representation holds true for the entire complex plane, and therefore we can have such expression for e to the z function. Now once again here I am writing the series for the function f of z is equal to ak into z minus z0 to the power k, and this time f of z I am writing as a sine function of z, and this sine function of z is analytic in the entire complex plane, and I am interested in the disk of radius r centered around z0, and here I prefer the center of the disk to be origin. And for this situation, f of z is equal to sine of z. This is the point where we are starting our discussion. Its first derivative of sine of z is cos of z, we have seen for complex numbers. And second order derivative of the function will be minus sine of z. Third order derivative will be minus cosine of z. Fourth order derivative will be sine of z, and so on. So you can evaluate the value of the function at the center of the disk, that is origin. So all the time here, if you look closely at these values, they are oscillating, rather they are cycling through 0, 1, 0, minus 1, 0, and so on. So here in fact we are interested in the AKs, and the first order derivative f dash at z0 upon k factorial. So here if you like to work out a0, a0 will be simply 0 because first derivative, rather zeroth derivative, same function we are writing at z0 and that has value 0. So first derivative, in fact, now we are talking about derivative here, a1, this is equal to the derivative at z0, that is unity upon 1 factorial. So 1 upon 1 factorial, this will be simply 1. Then a2, here we are taking second derivative, and second derivative at origin, it is vanishing. So a2 coefficient is disappearing. Then coefficient a3 I am talking about, the third derivative at z0 is -1. So this is equal to -1 upon 3 factorial. So this is 3 factorial and so on. You can go on working out this. Now here I have written sine of z is equal to this a0, you can relate, this is a1, a2, a3, a4 and so on and so forth. So here if you simplify this, it is z minus z cube upon 3 factorial plus z to the power 5 upon 5 factorial and so on. So this series you can sum up into the compact representation of series summation k rolling from 0 to infinity. So here I am interested in the odd numbers 3, 5, 7, 9. So I am writing z to the power 2k plus 1 upon 2k plus 1 factorial, and this fluctuating sign of odd coefficients I am writing as -1 to the k. So this is how the analytic sine function can be represented in terms of a power series. Now here we shall talk about the power series representation of cosine function z. So f of z is equal to cos of z, and this is an analytic function in the entire complex plane, and I am interested in writing the power series of cosine z centered around the center of the coordinate system, or say center of the complex plane. z0 I am choosing equal to 0. So here we obviously can roll through the similar step that we have followed in one of the earlier examples for sine, and otherwise I would like to write cos of z is equal to first order derivative of sine of z, and sine of z in the last example I have written as -1 to the k, z to the power 2k plus 1 divided by 2k plus 1 factorial. So here what all I can do is I can take this differentiation sign into the summation sign, and when I operate this, this is a constant term which has nothing to do with it, and function to the power n, we are having derivative of that, that becomes n times function to the power n minus 1. That's a usual formula we refer all the way, and that is true for complex numbers. So here 2k plus 1 times z to the 2k we are left with. So here we can cut one quantity here and one bracket here, and we are left with 2k factorial, and so we can write cosine function of z in the entire complex plane centered around origin as this series which is appearing on the screen. Thank you very much.